They say that learning's a bit of a journey, and I've certainly been on a bit of a journey with this particular calculation to determine the mean high water spring mark suitable for a land title survey. The scenario is a land title survey of valuable commercial land in Tauranga, and we wanted to find out mean high water springs. There's a number of options available in a document on the Land Information New Zealand website. A particular document here called Guidance Notes for the Determination of Mean High Water Mark and Land Title Surveys, compiled by Baker and Watkins. In this document, two methods, the Adduction Method and the Range Ratio Method, are illustrated. I, in my wisdom, thought that I'd go with the Adduction Method as it looked like the easier one to simulate. However, after my various searches for people who could help me with this, I had great difficulty in finding anyone who had any experience with this type of calculation in real life. And it wasn't until I got into contact with Glenn Rowe from the New Zealand Hydrographic Authority that I had someone who was able to guide me with the particular calculation. As it turns out, the most commonly used calculation is the range ratio calculation. So in the first instance, I tried to simulate the Adduction Method, and then as an adjunct to that, I ended up also including the range ratio method. So it ends up as a comparison of both methods. The first thing that we need to know is to get, in the first instance, the New Zealand Hydrographic Authority tide prediction tables. And these are used to determine or select 2 days when the predicted tide would be near the mean high water springs level suitable for cadastral purposes, and this is included in the document. So these are the prediction tables that are made available by the New Zealand Hydrographic Authority, and they are available on the Land Information New Zealand website. So we can get those there. In the course of this, it was quite difficult to correlate all the different datums, and it wasn't until I made contact with Glenn Rowe that I was able to get the valuable information that 0 for data from the Tauranga tide gauge is 3.586 below chart datum. 0 for chart datum and the predictions is 0.962 below Motoriki datum. Now, in the first instance, as I said, we used the prediction tables, and that we then, in our simulation or virtual simulation, we went to the site that we had chosen and set a random height pole in place so that we could take readings every 6 minutes about the tides on the days that we selected. And we were to use the Adduction Method to determine a mean high water springs suitable for use cadastral data set. Now, traditionally surveyors have referred to the cadastral data boundary as being mean high water mark. However, this is not the best description of what actually happens. And by definition, half of all tides will be above this mark. And so on these occasions, seawater will inundate the property, which is sort of against the wishes of the Registrar General of Land, who is a bit averse to issuing title to land that is underwater. So if the boundaries push, say, to mean high water springs, the problem doesn't go away, but it is reduced or minimised, as just half the spring tides, which occur twice a month or monthly in the East Coast, will exceed this level. But, on the other hand, some surveyors use physical evidence of tidal level, vegetation, etc. And when this is used, it's more likely to be that they are using the highest spring tide or the highest astronomical tide, which has an acronym called HAT. So moving on, I simulated a set of data by first of all taking the data from the Tauranga tide gauge. Now this minute by minute data is available through the LINZ website, but be very careful with the times, because the times used in the Tauranga tide gauge are Universal Coordinated Time, UTC, which was previously known as Greenwich Mean Time. Now the Greenwich Mean Time is 12 hours different from New Zealand's Standard Time, and when daylight saving is in place it can be up to 13 hours different. So the correlation of the times from the tide gauge data with local time and the timing of your calculations is very important and should be done very carefully, because it's very easy to get out of sync by a whole 12 hours or not allow for daylight saving in the correct way. So think about it very carefully. What I did was took the appropriate data from the Tauranga tide gauge and applied a random elevation shift to it, plus a small random change of between 0 and 9 millimeters. So the elevation shift was constant, and then plus a small random shift between 0 and 9 millimeters, just to put some variation into the data. I also shifted the phase of the data a little bit so that the high tide at the site and the control station didn't necessarily occur at the same time. So a little bit of a shift maybe of 12 minutes, I think was what I used, just to add a little bit more realism to the simulation. So here we have the simulated data that I have obtained via the Tauranga tide gauge data for 2 different days. We're going to look at each one and reduce the data or do the calculation. So just here we have the maximum observed height at the control station at 11:48, maximum observed height at the site at 12 noon. So I've just put a little bit of a phase shift in the data, in the simulated data there, just to make that happen. 12 minutes happen there. Now, once we had the data, of course, we plotted it up, and here we have the plots. I've just used Excel to do this. The red lines will be calculated later, as you see via the calculation. So there we've got our data plotted. Next thing to do is to start doing the calculation. Now at the reference station or the control point, we need to do this half-tide predicted calculation. This is done using the tide predictions, and I've done it here just to the nearest 0.1. So we take the information from them, it's meaned or averaged in that direction, and then the average of the average just comes out at 1 in this case. Now the spring range, this is again from information from the LINZ website, but you do have to be a little bit careful here. In the first instance, you can locate on the LINZ website the standard port tidal levels here, as you can see. But if you scroll down to the bottom of that page, you'll see that these are not intended for use for the determination of cadastral or administrative boundaries, and in fact it leads you to the page that is to be used for that, which is this tidal level information for surveyors, and this is the levels that you use to use. Again, it refers to adduction and range ratio methods and Baker and Watkins, so you know you're on the right page there where you get tidal level information for surveys. And if we just scroll down a little bit here just to look at the Tauranga data, we can see we've got a mean high water springs of 1.88 and a mean low water springs of 0.13. So back to our calculation, we can see here that we can calculate the spring range, again using that data, the half spring range of course, and then the mean tide level. Now moving on, we can go to our control station, and we're just following through some of the information. Mean high water springs is the 1.88 plus 3.586, which gives us mean high water springs at the control station, the 3.586 being the information that I obtained from Glen Rowe, and I've included at the front end of the document. Also, we now have the mean tide level above gauge 0, and again 4.596 using the information provided. So let's go. In the document, these here are numbers, and I've chosen to make them letters for more clarity, and I've shown them in red. I found the numbers a bit difficult to use as indicators, and sometimes easily confused during the calculations. Okay, it's now for us to, now that we have the information, it's now for us to look at the calculation. So we start putting in the information that we have, the high water predicted, the half tide predicted, the half the mean range here, and then doing the calculation here we are able to work out the range anomaly at the reference station. We now need to work out the range anomaly at the control station. The control station and the reference station are essentially the same in this instance. So again, we start with the half mean range, and the range anomaly of 0.12 here again comes out to be the same value, which is what we would expect. We have now our high water observed at the control station and the mean high water springs at the control station of 5.466, and this enables us to calculate the level anomaly of 0.144 by subtraction. Okay, now we go to the site. High water observed at the site is 6.813, and we need to look at the range anomaly at the site. To determine the range anomaly at the site, we must refer to the graph above. So first of all, we take the range anomaly that we have calculated at the control station, which is the 0.12 we've calculated, drop down from the highest point, draw a horizontal line to see where it contacts the graph, and scale it off, in this case 2 hours. We then apply the 2 hours up into our observation here, so we fit the 2 hours that we scaled there below, and then from that we scale from that line up to the highest point, and in this case we get a range anomaly of 0.12. So back to the calculation, plug in our range anomaly that we've determined at the site, and this enables us to determine mean high water springs of 6.549. Okay, we are now going to check our calculation using the range ratio method, and in the range ratio method we need to have another observation, and this is one that we've done. It's a minimum level of 5.01 was observed at the site, the same site, at the following low tide. So here it is. So there's our high water observed, which we've got before. Our low water observed again from the Tauranga tide gauge gives us our half tide level, our half range, this little piece of information here, and that enables us to determine our range ratio. We then go to the site. We've got our high water observed, which we've got before, and our low water at the site again observed. It's our half tide level, our half range times the range ratio, our mean tide level of 5.68, and then from that we're able to determine mean high water springs using the range ratio method. So we've got 6.55 there, and using the adduction method 6.549. So that's a reasonable correlation. The next thing we have to do is to now look at the the same thing for the next calculation. So away we go. We should now be quite familiar with the data. Here's our scaling again. Down to our calculation, we follow through exactly the same process. There's nothing terribly different at all. the only thing that happens is once we have determined our range anomaly here at the control station and go up to our graph to scale away, when we scale it back into the site we get a slightly bigger time and we get 0.13, a slight difference in our range, or what we're calling our range anomaly. So when we come back to the calculation, here we are, again follow through exactly the same process, put our range anomaly at the site in here, and we find we get a mean high water springs of 6.544. Again, checking this information using the range ratio method, we get 6.52. So slightly different, 20 mils different. And here we now just take the mean of our two that we've determined by the adduction method, and 6.547 is our mean high water springs. This is on the assumed datum at the site. It is thoroughly recommended that two benchmarks on solid land adjacent to the pole be established, and that the datum be established from the pole onto those other marks, so that the benefits of this work are not lost. So just to recap this situation, we have simulated the data by using the data from the Tauranga tide gauge to produce a set of observations with a slight little random factor into them. We have then used that information and other available information on the same site at two different dates using the adduction method and the range ratio method. We've gone through each one to determine the heights. We've got very reasonable answers which we consider to be acceptable. A slight difference, variation of no more than 20 to 30 mils, which on the face of it is quite reasonable. And this is for determining a level suitable for cadastral purposes. As a student, obviously finding real data in this case is difficult, so I have no problems with you simulating your own data and showing how you could use, or how this exercise would take place. And that's it. There you are.